Yeah, thank you very much. I think I'm blushing. I mean, everything you said was true, but nevertheless, I'm blushing. No, seriously, it's a great honor. It's really a great honor. Thank you so much, Bayer. Thank you so much, Selection Committee. I also would like to congratulate all my fellow award winners. It's really a great honor to be here, to be selected. Yeah, it's a celebration of science. I would like to quickly also thank my wife for driving me here. And for all the support she and my family provided me in all the years. I mean, thank you so much. I would like to thank the colleagues who nominated me, but also the wider community. I think it's so important to have a community, communities actually that work together, as you also mentioned. And I think that's what science, good science, I think is really about. And of course, last but not least, I really would like to thank my coworkers, present and former. You mentioned creativity. I think they are creative, and it's really team effort that basically leads to results. I would like to start. So I have 19 minutes for a quick scientific presentation to give you a flavor what we are working on. But I really would like to start with this image, The Good Doctor, as a TV recommendation. Watch this show, fantastic, heartwarming show of someone who's on the spectrum, who wants to become a surgeon. It's really wonderful. But I always like to also point out, to me, he looks like a chemist, but probably to most other people, he looks like a physician. So I think chemists, I mean, can a chemist be the good chemist? So that's me. So could there be a TV show on the good chemists? And I think that chemists are not good enough, maybe scientists in general, not good enough to communicating actually what they're really doing. I mean, in the end, we are really artists. In the case of chemistry, it's molecular artists. But like Michelangelo, I mean, creating the Pieta or this wonderful drawing, and each of them, I mean, being creative, doing something for the first time. And in chemistry, also doing something that really has a function. Not only being beautiful, but also something that can cure diseases or that can basically help plants to grow. I think this is really what science is about and what we have to communicate better. In my case, really wonderful laudatio, I was really amazed. We really work on many, many different topics. And for me, it's always difficult also to choose. We have around about 8 research areas, and the upper ones, they're really focusing on making molecules more efficiently using catalysis. But then also we have other research areas where we really try to make molecules for reason, functional molecules that we try to apply. I will try to give you a flavor of 5 different topics, and just one slide on 2 of them. N-heterocyclic carbenes, that's a class of organic molecules my group is very familiar with, and these molecules are really wonderful. They have extreme properties, and we are using them in 2 different areas. One is we take them and place them on surfaces, and they bind to surfaces very strongly, and with this we can modify the properties of the surfaces. The surfaces can be heterogeneous catalysts, so we can improve the catalytic performance. But these can also be devices that you have in your smartphone that maybe then get a better conductivity by putting the organic molecules on. This is an area I really like very much, and it's highly collaborative. So we have many partners, material science and physics. But then on the other hand, it's nearly the same class of molecule. If you compare basically the left and the right image, it's just a protonation that can lead to the molecules on the left-hand side. These are now positively charged molecules, and we put tails at the end of these molecules, and then they become lipid analogs. We can take more or less the same molecules and basically embed them in membranes and use them to modify the properties of membranes. We can either use this to study cholesterol and other lipids, but we can also use this to really have artificial function. I think that's really also the power of chemistry, that we can go to completely different functions with very, very similar molecules. And all of this we can make. Okay, I would like to start with failure. I would like to provoke you a bit. Failure really belongs to the scientific process. And as you will see, I believe in rational design, but I also believe in failure and new directions. I mean, Mark, really, you made the point. I mean, this is what science is about. So here you can read an email that I've received from a dear colleague, and more or less this colleague says that the work that I published doesn't work. It's shit. So at the same time, my group also wondered, how can we improve reproducibility? I will come back to this email in a second. But first, I would like to introduce you what we came up with to improve reproducibility of chemical procedures. So we think that a reason for reproducibility issues is often a lack of data. I mean, you have a procedure and you follow the procedure, but maybe the information that was given is lacking something. Or when you read it with your own background, maybe it sounds differently to you. So we thought maybe we have to be a bit more precise about certain parameters. For example, the temperature or the light intensity of photochemical reaction or the concentration. And maybe we should say run the reaction at 60 degrees, but maybe we should also say if you deviate with the temperature and go a bit higher, the reaction will really have a lower yield. Or if you go to a lower temperature, the reaction will have a lower yield. So investigate if small modifications, basically, of the parameters that we report have a significant impact. And we decided on 10 different parameters that we investigate. So here at the rim of this diagram, you can see these parameters, for example, higher concentration or lower concentration, higher reaction temperature or lower temperature. In case of the temperature, it would mean 10 degrees higher or 10 degrees lower. And then in this diagram, so here you can see results, basically. Each of these points tells you basically the outcome of the experiment. So the further to the outside, the lower the yield was. So here is the deviation is given. 0% would be the ideal reaction, the optimized reaction, and to the outside, lower yield. So in this case, if you go to a slightly higher temperature, basically, the reaction goes down. If you go to a slightly lower temperature, the reaction stays at the ideal, basically. So this tells you, if you try to reproduce the reaction, what you have to take care of. Okay, I would like to show you the application of this. So here on the left and on the right, you can see two chemical reactions. Both of them were invented in my lab. And if you would like to reproduce them, you would basically follow the procedure. But would you take special care of anything? How would you know what to be careful about? And now here I show you these additional information. Now you can see that the reaction on the left-hand side is very well behaved. For any of these parameters that we investigated, the deviations do not matter. It's a very robust, insensitive transformation. However, if you go to the reaction on the right-hand side, you can see, for example, that the higher oxygen content can kill the reaction completely. And also water and also lower temperature lead to greatly reduced yields. So this can really help basically to have a more qualified guess, basically, if you want to reproduce reactions. We've also shown that for different members of a substrate family, basically, you get the same results. So it always gives you the same pattern, basically, for different substrates of the same class. So now let's come back to the email that I've received. And this was more or less the same time, basically, when we developed this study. And the reaction is reproducible. In our hands, many others also reproduced it. But this particular group, they couldn't reproduce because they were not experts in the field. This is the diagram for this reaction. We determined this later on, not when we published, because we only developed this tool later on. And you can see that once again, the radar diagram looks different. In this case, the lower light intensity is the most critical factor. And this is basically what we told the colleague, because he said it fails completely. So most likely, if you look at this diagram, most likely the light intensity was too low. So we told him stronger LEDs are required. And then half a year later, he replied to me basically and said, we changed the lamps and now finally the reaction works. And I think this is probably a typical example. This colleague was not an expert for photochemical reactions, so he followed the procedure, looked for certain parameters, but was not aware that the light intensity is also important. And this simple knowledge can really help to improve the reproducibility of reactions. So you can really use this for many different things. So before you run a reaction, for troubleshooting, but also for data mining. And this is also what I like to talk about and think about, basically, where do ideas really come from? And so here you see my team of authors. Lena, for example, is also in the audience, first author, wonderful work. But then there's also Felix, and I think we have to give him the credit for coming up with this radar diagram, because he was a great fan of Pokemon. He actually went home to get this issue of Pokemon. And so the Pokemon characters, as you can see here, they are also represented using this radar diagram. So it's a very good way to represent data. And data, I mean, so we have a real data scientist here, also among the award winners. I'm not a real expert for data science. I mean, I try to become one, but I'm not there yet. From around about 10 years, my group has been interested in data, coming up with systematic methods to provide and generate data, like the robustness screen on the left-hand side, the sensitivity screen on the right that I've shown you. And then maybe 4 years ago, we've grown into machine learning, because we know about the data, we know about the problems in chemistry, and then a couple of really pioneers in my group have entered this field. And now we are really active in this. For example, recently we published a paper on the application of machine learning for a very, 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 very simple problem, the prediction of yields of chemical reactions. And the experts in the room probably know it's not that simple, because the reaction itself, A plus B to AB, that might look simple. But then if you look at the reaction conditions, all the many parameters that you can vary and then can have a dramatic effect, as I've just shown you in the sensitivity screen, all of these make it a multi-parameter problem. It's really a curse. So you can have the concentration, the time, the temperature, the solvent, the base, the additive, the ligand. All of them basically determine if reaction fails and also what kind of yield you get. So this being said, we investigated if one of the major databases, the Reaccess database basically, provides sufficient data to predict the yields of chemical reactions. And we found it does not. It's not possible. So we investigated this for 4 very prominent reactions, but more or less the result is a negative one. A negative one, and we also understand where the problem is. I will tell this to you in a second. But now it can basically guide us for the future, basically. Guide us towards the information that we need to gather in order to feed machine learning. So we found that there are 3 main problems. The first one is the least important. The data is often not very accurate. So the yields, they might be a bit higher, a bit lower. It's not exactly the right yield in many cases. The 2 problems on the right-hand side, they are more dramatic. The one in the middle, biased experiment selection. So the scientists who feed the databases, basically, they always like to use their workhorse systems. Always the same catalyst, always the same ligand. And this leads to clustered data. Already the space is huge, but then the cluster, the data that we have is clustered. So then there are other areas that are even more empty, basically. And on the right-hand side, this is the lack of negative data. How can a machine learn about chemistry if you don't tell a machine that reactions can also fail? If you look at the distribution of yields in Reaccess, then you will see that the higher yields are more common than the lower yields. And this is really opposite to what any chemist who ever worked in the lab finds. So it's basically not the truth. negative data is lacking. And so this will take a community effort to overcome these limitations. And as you also rightly pointed out, at the beginning of the pandemic, I started an online series of symposia on molecular machine learning, bringing together people from very different disciplines. And this is the one from last week. I think it's very important that we talk about what kind of data would be useful to have, and then it's a long-term process. Then really start basically this endeavor. Okay, I would like to talk a bit about discovery because this is really at my heart, and I always like to start with two quotations of two real experts. The first one is by Mike Tyson, world heavyweight boxing champion. And he said about discovery, every man has a plan until he gets punched in the face. And this is very true, as you all know, as is the statement by Woodward. And it's more or less the same statement. So Woodward was asked, shortly before his death, he was asked if a reaction that he basically reported on was rationally designed or a serendipitous finding. And then he said, yes, it was a planned reaction, just like the 25 others that we tried before that failed. And it's really the perception. No? So we have an idea, at once in a while we are lucky and succeed. And then we tell the story based on this. No? We say, oh, we had a great idea and we know rational design. But we forget to see all the failures. And I think it's very important to see this. Okay, I would, in my opinion, rational design and experimental finding, these are probably the extremes. Rational design, I have a fantastic idea, I go to the lab, it works out. Experimental findings, something unexpected happens. And then you start the process based on this. I would like to tell you basically two rational design findings, and I would also like to show you a strategy how we in my group try to make experimental findings in a more rapid fashion. Okay, just one slide on the first finding. So this we published last year in Nature, and it's a very simple deviation from what was known. It's about a photochemical reaction in which you basically take, typically would take two olefins, two double bonds. One double bond and a second double bond, and then you can excite them with a light, and then you get a photochemical reaction and the formation of a four-membered ring. We wondered, can't you use a strained single bond, as you can see in this molecule? This is called a bicyclobutane, and this bond that's highlighted is a strained bond. And the rational design was basically, let's use this, a formal single bond basically, and react it with a double bond. And then this will open and we will get a five-membered ring. So 2 plus this 1 basically giving us this five-membered ring. And this worked out beautifully and is now also really the starting point for a new research program that we have in my group. Another rational design I like very much. And it starts with research of a fantastic colleague, David O'Hagan in St Andrews in Scotland. And he published this Nature Chemistry paper, and his molecule, the molecule that he made it to the cover. It's really beautiful. It contains of 6 carbon, 6 hydrogen, and 6 fluorine atoms. So the fluorine atoms are the green entities, and fluorine also plays a very important role in drugs because it really changes the properties, like improves the metabolic stability, changes the polarity. What he succeeded with is making this molecule for the first time, the all-cis hexafluorocyclohexane. It looks like a crown. All the fluorine atoms point to the same face. It's the most polar organic molecule. I heard him talk in Valencia in probably 2016. And he said, it's a wonderful molecule, but then I got contacted by NASA. I mean, this is once in a lifetime. NASA contacts you and wants your help. Houston, we have a problem. And then NASA wanted some of the molecule, some of the compound. But he David O'Hagan, couldn't deliver because he made only less than 1 milligram of this compound. It is a 12-step synthesis to make this molecule. He couldn't deliver. That's frustration of his life. So I met him, and at the same meeting, basically, I spoke about rehydrogenation. And I wondered, actually, we also went for a walk and we discussed, and I wondered, shouldn't arene hydrogenation be suitable to basically give us this cis stereochemistry and the saturation from readily available starting materials. So starting from a fluoroarene, basically doing the hydrogenation and getting to the fluorinated saturated ring system. However, the problem is, if you look in the literature, then you will find that hydrogenation will cleave the carbon-fluorine bond. So it's really a sensitivity problem. Will the carbon-fluorine bond survive while you do the job, the arene hydrogenation, or not? And then Mario, also in the audience, basically led this endeavor. And this is now the Game of Thrones, because we use rhodium as a catalytically active metal. And once again, we are also standing on the shoulders of giants. So we had this rational approach, and then we looked into literature which catalysts could be suitable. And we basically decided, amongst others, on this rhodium carbene complex. Once again, carbenes, the molecules that I mentioned at the beginning for the on-surface and the membrane chemistry. And it's a special kind of carbene, one that is only having one nitrogen in the ring. And these were developed by Guy Bertrand. He's a pioneer in carbene research. And he developed these. A postdoc of his went to China, became a professor, developed this rhodium catalyst, also used this for arene hydrogenation. And then we used it for our study. And here you can see the results, and it works beautifully. However, the conditions are really key to success. So it's not only the catalyst, but also the molecular sieves and the hexane. The apolar solvent is crucial for success. If you use a polar solvent, you will get the cleavage. If you use an apolar solvent, you can succeed. And this basically led to many examples that we basically applied this method to. And then here in the center of the slide, you can also see the hexafluorocyclohexane that we could make. And we could make it in one step, basically from commercially available starting material in 80 end yield. So this is really nice. Of course, I also told this to David O'Hagan, and then he also contacted NASA, true story, but they moved on. Now they want to go to Mars or so. Okay, and this is the photo of the team, wonderful team, great paper. Okay, I see I have 3 minutes left, and I think 20 slides. So we are not at the end. Experimental findings. This is really something that's bothering me. There are often these serendipitous findings, and you mentioned Ian Fleming's penicillin. And how do you make a serendipitous finding? The definition of serendipitous finding is you look for something, but then you find something else. The definition is not you look for nothing. And I think, why do we have to look for something else? Why can't you be really focused on this discovery process? And in my opinion, this is screening. Smart screening technology. And many in the community actually don't regard this highly. They think, oh, screening is stupid, basically. But I feel the opposite. A really smart screening strategy is probably the most difficult thing you can build. So here you can see a well plate. Don't look at the text. It's just a well plate. And you can basically vary the conditions. For example, for a catalytic reaction, you can vary metals and ligands. And then you will get results or you will not. Okay, this would be a standard strategy. We came up with a new strategy, and we are still thinking about new strategies. So this is not, by no means, a finished process. And we coined this term as catalyst speed dating. So we want to find new transformations, and we want the catalyst to identify one substrate for this reaction. So we want the reaction A plus B to work, and we want the catalyst to find which compound could act as a suitable substrate, catalyst speed dating. In the first time we did this, we applied it to photoredox catalysis. You can use certain catalysts, basically transition metal catalysts or organic dyes, basically. They take up the energy of visible light. You also mentioned this, and they become excited. And then if they pass on this energy to organic molecules, a catalytic reaction can start. So now we want to identify the molecules they can pass the energy on as opposed to the ones that don't care, basically that don't interact with the catalyst. And so here you can see basically the luminescence basically that an excited catalyst, so when the catalyst gets excited and does not find a partner to pass on the energy, then the catalyst will go back to ground state and it will emit light. And here you can see this emission spectrum of this unsuccessful catalytic reaction. And now I add a molecule that can interact. And then the emission gets quenched. So this is a hit, this is a success basically. This organic molecule that I've basically used together with the catalyst could potentially be used as a suitable substrate. Okay, and this we basically did, and we identified new substrates, and we could also develop transformations based on this. I would like to point out that you can also use other analytical tools basically to identify this kind of catalyst substrate interactions, for example, mass spectrometry or voltammetry. But also, and this is now the end of my talk, also show you how we use this basically to identify two partners of a new reaction, and both by individual screening events. So here you can see a catalytic cycle that in the end we want to achieve. And the substrate A we can identify with our mechanism-based screen, with the catalyst speed dating. So luminescence quenching of 100 or 1,000 substrates, we identify the one basically that quenches and interacts with the catalyst. And then to identify a partner, a suitable partner, we use the traditional screening. So we use the catalyst and the substrate we identified, and now we screen basically a huge number of other substrate partners B as a possible partner. And this would be represented by this well plate. And so here you can see substrates we identified in the first screen, then we add other partners for the second, and each of these green spots corresponds to a new chemical transformation that was not reported before. And I think it's really a wonderful strategy to identify new reactions, to discover basically rapidly. Okay, this is it. Invite me another time for another award. I'm an organic chemist and I really love molecules, and I love this photo actually. Thank you so much for the funding agencies, for the Bayer Foundation, and for all my co-workers. Thank you so much.